a multi-rack? Okay, what is a multi-rack configuration? So typically in a data center, what you have multiple racks, right? So that is how your servers will be stacked across. So you have multiple racks. Just visualize you have 3 different racks and 3 racks, and you have 4 servers in each rack. Okay, 4 servers in each rack. Three more servers. Just trying to have a data center architecture, trying to write up here 2, 3, 4. So 1, 2. Okay, now what you have here, you have in terms of rack 1, this is rack 2, and this is your rack 3. Okay, so you have a data node here, DN1, so 2, data node 3, data node 4, data node 5, data node 6, data node 7, data node 8, then 9, 10, 11, and 12. Okay, so consider, just visualize you have a 12 node cluster stacked across multiple racks. Now what will happen here is when you upload your data into your HDFS, okay, when you upload your data into HDFS, say for example, let's say your there are 3 blocks, okay. Block 1. I'm just trying to do a color coding here. Then you have block 2. Then you have green, we already did, let's say blue. Block 3. Okay, so you have 3 blocks, block 1, block 2, and block 3. Now what will happen here is when you upload this file, your file is made up of 3 blocks. Say for example you have a 150 MB file. So how many blocks you will have? You have 3 blocks, 64 MB considering the default block size. 64 MB, 64 MB, and remaining 22 MB, right? So this is block 1 is 64 MB, block 2 is 64 MB, and block 3 is 22 MB. Now let's start writing this data. How does the write happens into the cluster? We talked about 3x replication, right? We talked about data being replicated 3 times. Now when you have 3x replication happening, okay, so how does this get written here? So the data will be written in such a way that the block, blue is already highlighted. So one block, one replica will be on one machine, and 2 replicas will be on on a second rack. Okay. Now similarly, you have you may have block here, block 1. Then you may have block 1 and block 1, and finally your block 2. Block 2 can be, sorry, oops, I think add block 1. Okay, sorry guys, this should be block 3. Okay, this blue is block 3. Okay, let me block 1 I have written here. Block 2, let me write block 2 also. Okay, let's write block 2 here. Block 2, 1 replica is written here. 2 replicas will go in here, and the third replica. Okay, I don't think I have an erase. I cannot erase this. Okay, let me just drag this out. Easiest way. This is block 3. Block 3 would be written in such a way that, let's say, let's go block 3, and 2 replicas will go in here. So I have just don't worry about this part. These things are all, you can ignore this right now. Now let's see here. I have 3 blocks, okay, color coded. Block 1 is green, block 2 is orange, and block 3 is blue color. Okay, so when you copy the data, we talked about 3x replication. Now if you see here, anywhere you see one block, okay, there will be one block on one rack, and the two succeeding blocks will be on a second rack. Okay, look for block 1. Block 1, one block is on rack 1, and 2 successive blocks or 2 replicas, right? The second replica and the third replica goes into rack 1. Similarly, you have block 2. Block 2, one replica is on rack 1, other replicas are on rack 3. Similarly, rack on block 3, one replica is here, and 2 succeeding replicas are on second rack. Now, the rack awareness algorithm or rack configuration algorithm is in such a way that one block will always be on one rack, on a server on one rack, and the succeeding and the replicas will be on a second rack, but on 2 different servers. Okay, so this is how the data will be copied over. Now we may have a question: why not implement? Okay, why not copy this block into a third rack? Okay, now one more thing you can notice is, if any rack goes at any point of time, if any single rack goes, you always have the ability to recover the data. Because say for example rack 3 crashes, okay, the entire rack 3 is not available. So what you can do, you can access, you still have block 1. Okay, block 1 is here, block 2, at least one block is available on a different rack. So when the companies decide on a rack awareness, or how they configure your clusters, they will consider all this into picture. Okay, this is your entire Hadoop cluster. So this is your entire Hadoop cluster, which will be, the data will be stacked across multiple racks and multiple servers across multiple racks. Now the question can come, why not use all the 3 racks, because you have 3 racks. Okay, why do you have to copy the third replica in the same server, in the same rack as your replica 2? The reason because when the data node copies, when the client copies one block here, the first objective is to write the block as soon as possible. Okay, to write the block as soon as possible. The next objective is to make sure, what if this server crashes, right? What if the server crashes? I don't have a redundancy. So what you do, you copy it onto a second server, okay, onto a different server. Now the third objective is, that's right, Hemal. Block is a collocation of data. You can say my file is made up of. It's a 150 MB file. Okay, it's a 150 MB file. It's made up of 64 MB block, 64 MB block, and 22 MB block. So let me put this all together. Your 150 MB file is made up of 3 blocks. When you start writing the data in here, this is how the data will be distributed across multiple racks. Okay, so I was saying the second block's objective is for redundancy, to make sure it is available and it will be copied onto a second server. Okay, and also make sure that it is copied onto a machine. Okay, it is copied on a machine which is not on the same rack. Now the third block's objective is, what if these two servers crash? What if this rack crashes? And what if even this server also crash? So to make sure it is highly available, a third block will be copied over. The third replica will be done. The third replica is copied onto a different machine. Now we may have a question, why not this third replica go into the third rack? The important thing to note is the communication between the servers is very fast. Okay, the communication between the servers within a rack is very fast than the communication, okay, between the servers in between the racks. So within the rack communication, right? Yeah, Ashu, I'll come to that. Okay, so the communication within the rack is faster, and what will also happen here is you will have something called as a top of the rack switch here. This is how the racks communicate with each other. Okay, so this is called as TOR. Let me put it this way. TOR is nothing but okay. So this top of the rack switch will be available. This is actually, it should go within the rack, guys. It should be this rack. The top of the rack switch should be within the rack. It should be inside this rack. So when the communication between the racks happen, or the message, so this block, what it has to do, when the block is, the first replica is written here. When it wants to write into a second server, okay, the replica, it goes to the top of the rack switch. From here, it goes to the top of the rack switch on the rack 2, and from here it goes and writes here. So what you do here, you are occupying the network bandwidth, right? You're occupying the network bandwidth, and here if you copy within this rack itself, you're not occupying any network bandwidth. Now you have to remember that the network bandwidth is expensive, right? The network bandwidth is expensive. You need to invest heavily for your network bandwidth, and you're making sure that you're avoiding one additional hop here. Okay, and it is we are not talking about a very small files. We are talking about huge amount of files, right? We are talking about forget about gigabytes. We are talking about petabytes and terabytes and petabyte scale of data. Just imagine if you want to copy so much of data, so much of network bandwidth is unnecessarily utilized to copy the third replica from your rack 1 into rack 3. So to avoid one additional hop, to avoid one additional network bandwidth, it will be, this is how the data is structured, and this is how the data is replicated across all the nodes. Now, a couple of questions which came in. What if rack power loss? So rack power loss, yes, Ashu, rack power loss will be there, okay, but again, companies invest heavily to get these racks, and even the companies spend more money, or companies will provide you a HA for the rack. There will always be dual power supplies. There will always be dual Ethernets. There will always be high availability available for each of the racks. But it's a rare scenario if the rack fails. Okay, just visualize if this rack is failed. If this rack fails, but I still have the data being retrieved from some other blocks available. Okay, so you'll have the data. You can retrieve the data. You can. So in this case, in this example, I have 12 servers, which I have distributed across multiple racks, and I have the ability, I can sustain a 1 rack failure, but I cannot sustain a 2 rack failure. If even this rack fails, right, I am losing the data. right? Even if this rack is going to fail, I'm losing out the data of block 3. Block 3 is not available. Somehow I can retrieve block 1, but block 3, okay, block 2 and block 1 I can retrieve, but block 3 I cannot retrieve, because these two racks have this. So rack failure is a very rare scenario in a highly sophisticated data center, okay, in a properly maintained data center. But they build the assumption that because we are building up a commodity hardwares, okay. So we talked about commodity hardware in our initial sessions, right? So what is a commodity hardware? Commodity hardware is a cheaper hardware. It's not a cheap hardware, it's a cheaper, which falls in between your lowest range of servers and topmost range of servers. When I say lowest range of servers, it could be your desktop and your laptops will be at towards the bottom towards the cost graph, and your high-end servers, your carrier class server or your enterprise class servers will be towards the top. It will be very expensive. So in between your your carrier class and your laptops and desktops, you have something called as a commodity hardware. So the assumption was, because you're investing in a cheaper hardware, this hardware is going to fail some point of time. That's why they build that replication factor. Okay, so this is not a high-end hardware. It is going to fail at some point of time. So to make sure that the failure is addressed, you're building up multiple blocks. You're copying multiple blocks into multiple servers. So this is how the entire rack awareness algorithm will work. When you implement a rack awareness algorithm, this is how the data will be distributed across all the nodes. Other question is how racks got distributed. The racks got distributed. You as an admin, the administrator will decide on how the data nodes should be going into which rack. Okay, all this needs to be planned. Okay, before you start the cluster, before you do the installation steps and all this should be planned. And you as an admin will need to make sure the data is distributed across all the nodes, and the data nodes are distributed across all the racks. And even then, once the data nodes are spread across multiple racks. Now tomorrow, if you want to add additional node into the cluster, it is always suggested that you add 3 other nodes. Okay, so that rack 1, rack 2, rack 3 will get their own nodes. Rather than simply adding a node into one rack, if you add 3 nodes, okay, it will make sure that the data is balanced equally across all the racks in the cluster. The end objective is to make sure your data is balanced. Okay, the data is balanced across all the nodes in the cluster. Nice. Any questions on this?
This is Madhu here. I have a question regarding the replication of the data. So the algorithm is supposed to distribute the data, or that is a setting that the admin is going to control and they have the ability to make changes?
The distributing the replication, only the replication is done internally by the name node. Okay, so administrator will not do any changes here. It's all taken care by the framework itself. Okay, so I said that 2 blocks will go here. So you as an administrator will not have any say in which node should go, which node should have second block or a second replica. It's all taken care by the framework. Now, when I say the framework, it's a name node. When I say the name node, the data nodes will give a heartbeat message to the name node every 3 seconds, right? So in that heartbeat, depends on that heartbeat. So name node will see that what are all the data nodes available for me, what is the disk space on those nodes, is the data node ready to take the data or not. Based on that availability is what the name node decides. So that's what the framework will take care of, copying the data across or distributing the data across multiple nodes in the cluster. So admin's role will be limited there. There is no role at all for admin when the data gets distributed. The admin's role is only a physical thing, a physical mapping. When you build your multiple data nodes, you as an admin will need to make sure these data nodes are stacked across multiple racks. So there ends your admin's job. Now everything is inbuilt. Okay, the rack awareness is an algorithm you need to enable, which is a logical thing. So for a rack awareness thing, it's a 2 things. One is a physical mapping. The second one is a logical mapping. Physical mapping is you decide, you see what is the rack, what is the server going in. Logical mapping is the same thing. Whatever you have mapped, you are indicating in a file, you are indicating in an algorithm to the name node. These are the racks available. These are the nodes available. These are structured across all the different racks. Now, if you don't enable rack algorithm, what will happen? The name node will consider everything as a default rack. It considers it as a default rack, and the data will be arbitrarily distributed. Okay, the data will be randomly sent across all the nodes. So in those situations, you may end up in having one rack getting more data, and the second rack will not be having, maybe having very less data. So to avoid that situation, they came up with this rack awareness where the data will be always distributed across all the nodes equally.
Okay.
Does it answer your question, Madhu?
Yes. Well, I have one more question. Do we have the capability to change that algorithm, or we just have to put some numbers and say this is what we want? Just an overview will be fine.
See, as an administrator, you you can write a simple script. Okay, you can write a simple script. Normally, what will happen is if you want to say implementing, how you implement is just say the IP addresses. So I have 192.168.1.1. Then I have let me copy this. 2. Then I have 3. I have 4, 5, 6, 7, and 8 servers. So I have 8 servers. What you need to do, you need to create one text file. Create a text file. And then within this text file, okay, just say topology.text. Within this, you are saying my server 1 is on rack 1. Okay, let's say, typically you can figure out this information from your configuration management tool. Companies implement Service Manager, then they have Remedy, then they have various tools, right? So it is where you can actually pick it up from. So it can be on switch. This is how, I'm just giving an example, guys. This is not exactly how it will be done. SWF, SW switch, and let's say it's a data center 1, and within that you have a rack 1. So this is how the mapping is happening. So you can pick this information from your configuration management tool. Now, if you go and see your configuration management tool, you'll see that each of the server will be assigned an IP address, and it will also be assigned a rack name. Okay, if you have the servers stacked across multiple racks, that is how the servers are identified by your data center technicians. Right? See, you do not have access to the data center. You want to reboot a server. You want to do a physical reboot. What you do, you contact your data center support. The data center support will pull out your configuration management and see the server IP address and see where the server is located, on which rack, on which switch, on which data center. They take with that. One second, guys. With those details, they contact they go inside the data center, and then they locate it, they liquid the server, that IP address, and restart it. So the same thing is what you are writing into a text file. Okay, this mapping should be done. Once this mapping is done, you write a simple algorithm. Okay, a simple shell file. Okay, shell file. I don't have the algorithm right now, so which will. Okay, I'm just giving a pseudo code. Okay, read the file. Okay, read the file topology.text. Okay, and step 1. Step 2 is if the IP address is okay, read the file topology.text, read line by line. If the IP address is matching, then give the rack name. If the IP address does not match, then give the then consider it as a default rack. Okay, simple 3 lines. Or I mean, algorithm is different. You write a while loop. So what it is doing is you are reading line by line. So first server name node will see this IP address and sees whether this IP address, okay, first IP address is available. Now this IP address is there in this topology.txt file. It will do a mapping here. Now if there are other servers, okay, tomorrow you add one more server, but you did not add this into topology.txt file. When the name node encounters that server, it needs to see where this is available, okay, on which rack this is available. With that IP address, it goes and tries to read the topology.txt and sees if it is matching in here. If it matches, yes, it knows that this is on rack. Okay, so let's not put into rack 1. This is in rack 2, rack 3, and this is in rack 4. Okay, so this is how the data is. This is how the data nodes will be distributed across. And if that IP address is not available in this text file, okay, in this text file, then it will consider it to be a default rack. So your 3 replications will follow this rack topology. Now you can implement more than 3 replications also. When you implement more than 3 replications, the next replications will be arbitrarily copied. But for the 3 replications, this is the algorithm which is followed. Oh, sorry guys, I think just clicked on mute. Right, so you can increase the replication with this property, which is dfs.replication. Now, can you tell me which file will this property go inside? dfs.replication is a property which will set your replications. So you have a property. Can you guys tell me on which file this will be available? On which file? Replication is what? Come on, guys. It's a name. Just replication is related to what? Replication is related to HDFS. So which file should it go? It should go inside. Right? This will go inside your HDFS site.xml file. Okay. So you add a property dfs.replication and you put a value here, either 3 or you can say 4 or we can say 5, whichever value you put. So by default it is 3x replication. If you don't define this property in your HDFS.xml, it will automatically pick up your 3x replication. Okay, so this is how, this is the importance of the XML files. Okay, this is the importance of your XML files and how you can play around with your properties and you can set the replications also. Now there is also property by the name block size, right? dfs.block size. dfs block size is 64 MB by default is what I've been saying. Now you want to change the block size to 128 MB. Okay, so where does this property go? This is also related to what? This is also related to your HDFS, right? dfs.blockSize is what? It is a property related to HDFS, so it will also go inside your HDFS.xml. So your replication factor you can change, your block size you can change. You have the ability as an administrator to decide on what sizes you can set. Okay, guys, clear until here? Okay, let me save as an image. Now, so we have 10 more minutes. Let me quickly talk about checkpointing part. Okay, checkpointing is very, very important. Checkpointing is an important feature of Hadoop. So what we said was your name node. Okay, so you have a name node, and just take do an exact copy of this. And you have a secondary name node, right? Have a name node and secondary name node. So on the name node, your metadata will be written in two files is what I said, right? One file is your FS image. FS image is what we have seen earlier, right? FS image. And the second file is what we talked about is edits log file. Edits file. So when the end user, when the developer writes a file into the name node, what does it go? The metadata information will be residing on your FS edits file. So it's similar to your transaction log. Okay, this is similar to your transaction log. The data will go and reside. I mean, the metadata will be on your edits log file. Now, as the metadata keeps on increasing, the size of your edits log file will keep on increasing. Now, you need at some point of time, you need someone to combine these together. Now you have a secondary name node with Hadoop 1. What I said was secondary name node will pick up the metadata every 1 hour, right? So every 1 hour, what does a secondary name node do? Secondary name node will say, contact your name node, give me the metadata, I will keep it as a backup. So it contacts, okay, it contacts your name node and picks up the metadata here. And then what does it do? It copies both your FS image and edits file, and then it will make it a bigger file. Okay, so okay, let me just copy this first. Edits and your FS image. Okay. Now what this will do is this will combine this. Apart from copying these two together every 1 hour, it is going to merge these two together. Okay, this will be merging these edits file and your FS image file. So your FS image, and this is copied. Secondary name node contacted the name node and says, give me the metadata. It took the metadata, and once it gets the metadata, it copies this together. Okay, it copies and combines this together, and then it will make an intermediary file called as fs image.ckpt. A checkpoint file will be created. Okay, a checkpoint file will be created. Now what this checkpoint file is? Checkpoint file is a bigger file which has got all the incremental additions for the last 1 hour, right? For the last 1 hour, whatever data you have written into edits has been copied over. So that goes into your fsimage.checkpoint file. Now this fsimage checkpoint file will be copied back, okay, will be copied back into the name node as a fsimage. Will be copied back here. Now, say for example, if this is about 100 MB and in the last 1 hour you have written some data and your metadata has increased to about 50 MB. Now, what you will have a 150 MB file, right? So this is rolled into an FS image file. Now, at the same time, while this edits file is being copied over, what it will happen is the name node will convert this edits into an edits.new. It will roll this edits into an edits.new, so that so that people can still write into the cluster while this process of checkpointing is happening. Okay, all the new information will be written into all the new metadata. If there is, I mean, while this process is happening, if there is a new file which is coming to the cluster, that goes into your edits.new. Okay, now once the FS image has been copied back here, the bigger FS image has been copied back here, your edits.new will be rolled back into your edits file. Okay, will be rolled back into the edits file. Now you're back to the square one in the same state. Now this process keeps on happening every 1 hour, and that process is called as checkpointing. Okay, this is nothing but checkpointing. So if I want to repeat the steps, checkpointing is the secondary name node contacts name node every 1 hour, picks up the metadata. The metadata is your FS image and edits file. They combine this together into an FS image checkpoint. This checkpoint file is, so you have a bigger FS image file. It is copied back into the name node. You have a bigger FS image file, and while this is being copying, you have a new edits file created. This is an empty edits file. This empty edits file will be rolled into a new file, and you have an edits file here. So this is the process of checkpointing, and this cycle keeps on repeating every 1 hour. Okay, every 1 hour. Now there is disadvantage with this is if the name node crashes. Right now my time is about 7:27. Okay, for my time is 7:27. Around 7 o'clock, say secondary name node has picked up the metadata, and around 7:30, if the name node crashes, you can recover the metadata, right? You can recover the metadata until the point where it has copied. That is till 7 a.m. After that, it has crashed. So you always have a risk of losing the data at least for a minimum for at least 1 hour. You have a risk of losing 1 hour metadata. When I say the metadata, when the metadata is not available, that means the data is of no use, though you copy it onto your cluster, right? The data is available, but if there is no mapping happening, then the blocks are of no use for you. Guys, clear until this? Clear with checkpointing part?
Yes. I have a question on this. So can't we, reduce the time limit for that instead of copying it in every hour? Can't we copy in 30 minutes or 20 minutes?
Yes, you can do that. Yeah, you can do that.
Okay.
The problem here is, see the name node. So what is this? This is a request to the name node, right? So the name node is the brain of your cluster. Name node should be catering to, should be available for the data nodes to give their heartbeat message. If there are 100 name nodes, sorry, if there are 100 data nodes, then 100 data nodes will open up 100 threads and give in a message to the name node. Now the name node is also the guy responsible for accepting the developer request. Somebody may want to read a file, somebody may want to write a file, then your name node will be overburdened. If you increase this, if you reduce the time limit, you are adding in additional burden on the name node. Okay, because the number of threads the name node has to open up is more. So that's a disadvantage, primary disadvantage with Hadoop 1. Okay, this is what with Hadoop 1. So to overcome this, they came up with something called as a standby name node with Hadoop 2. Okay, they came up with something called as a standby name node. So in Hadoop 2, you would not see secondary name node, you will see a standby name node. I think this is what we talked about with HA feature, right? The HA feature is what we talked earlier in our second class or third class, where I told you of the different features of Hadoop 2. So you will use standby name node, as the name itself indicates, it's not a secondary name node, it's a standby, which means it is highly available. So the secondary name node is not a hot standby. Okay, I think most of your database guys, you know what is a hot standby and what is a cold standby, right? But this process of checkpointing will remain the same irrespective of it is Hadoop 1 or Hadoop 2. Now with Hadoop 2, you have a second standby name node implemented. So the process of checkpointing will be done by, has been delegated to standby node, and there is no secondary name node.